So today we'll start the main material of the course. Main as in like we're going to begin getting our methods that we want to acquire throughout the course. And we start by humbly going back to algebra, which I think will provide us very, very good tools that are going to be useful throughout the course. Some of it can be a review, some of it can be new. So, but even if it feels like a review, the nature of algebra is such that you can go over the same material like twice, 3 times, 5 times, and still learn each time. And I encourage you to not see it as a waste of time, but instead as an opportunity to polish details. Algebra just works this way. You have to do iteratively go through the material to learn better. All right. So this time, least squares, null space, row space projectors. Okay. So least squares will devote the whole lecture to it later, but let me give you like an idea, like at a glance, what least squares is on the high level, if you want. So assume you have a problem. The problem is to find the smallest norm x. Smallest norm we understand as a 2 norm. I don't say it here because partly because when we don't say which norm it is always 2 norm. Part because it's it doesn't figure in the slides. We'll talk about it explicitly when we discuss least squares later. But anyway, smallest norm x, and you have this equality ax equal to y. And you want to find such smallest norm x that this one has a least residual. So least residual is a constraint, if you want. The smallest possible residual is, of course, 0. But sometimes if it doesn't have a solution, exact solution, the residual cannot be 0. In this case, you'll have to find such x that the residual is as small as it can be. And out of all such x, you want to find the one with the smallest norm. So this is a problem. We call it least squares problem. And it has a solution. Numeric solution if you want, or exact solution, but here it is.
What A plus means?
Yeah, that's what I'm going to discuss right now. So this this symbol here denotes a pseudo inverse. We call it sometimes Moore-Penrose pseudo inverse, and but in practice, I have never seen anyone at the classrooms use any other pseudo inverses. So just call it a pseudo inverse. Okay, so pseudo inverse. There is a number of ways to answer what it is. Like one way is to say, okay, there's a formula, and I don't know if I want to write it like from memory, but there is an explicit formula that would be something close to. I mean, never do math from memory, but I think that the formula will be something like this. So this would be like a pseudo inverse formula for this A plus. No one uses this formula to compute it though. Like, why? Because this procedure is ill-defined. Like how are you going to compute inverse matrix? Of course, there is a definition, right? You can do Gaussian elimination or whatever. There are ways to compute it, but they're computationally unstable, long, difficult. No one uses this basically. Like no one computes inverses. So therefore, like saying that this is a definition of pseudo inverse is just academic. It's interesting, but it is academic. We will get to this formula later. Like you would see how this formula is derived. So no problem for now. Right. Another way to say it is that this is just some magical matrix which you can compute And in practice, you compute it by saying, let's say, in Python np.linalg.ping. That is how you compute it. It's just something that you compute using NumPy. Okay, unsatisfying, mathematically unsatisfying, but that's how we do it in practice. What NumPy actually does here, it computes SVD decomposition of A and does some rearrangements. So you will see it too in a while. But what I'm trying to say is there are a few ways to think about pseudo-inverse. But I think the best way to think about pseudo-inverse is actually to say that pseudo-inverse is just a solution of least squares equation. So you have a least squares problem. Its solution is this solution here. Let me just clear all the drawings. Give me a second. So its solution, as given here, is just a consequence of that is what pseudo-inverse is. You look at this equation 1, and this matrix here that provides you a solution to the pseudo-inverse problem is, to the least squares problem is a pseudo-inverse. That's it. How you compute it is a different story, but the definition of it is just a matrix that gives you a solution to least squares. That is useful because there is a tight connection between least squares and pseudo-inverse. Okay. By the way, why pseudo-inverse? Well, because if there was exact solution, so there was there existed such an x that ax minus y is equal to 0, then you can say that x is equal to -1, right? Maybe. If there existed, yeah, I guess this is by the way incorrect. What I said just now is, I think, incorrect. There is sorry about that. Let me just write it correctly. If there existed, yeah, okay. Let me just write it separately here, and we'll return here. If there existed inverse of the A, then you can just say that x is equal to A inverse y. Okay. If it doesn't exist, so if determinant of A is equal to 0, if A, for example, is not a square matrix, which is a typical, but then there exists such A that this is true, then you can still write it as such, right? But you cannot write it as such. Like this is not applicable to this case. But that's what I'm trying to say, I guess. This very satisfying formulation, where you can clearly see that x is a solution to this system of linear equations, does not apply when determinant of A is equal to 0. But there can still be a 0 residual solution, like here, for example. There exists such an A that such an x that x minus y is equal to 0, and x is a 0 residual solution. It's still given by pseudo-inverse because inverse doesn't exist. Maybe A doesn't exist actually. X doesn't exist, so there are no 0 residual solutions. You can still find x which gives you the smallest residual solution. So that is the whole story for least squares, and that is exactly the role pseudo-inverse plays here. All right, don't worry about pseudo-inverse too much. We'll use it again and again and again, and feel free to read up on it on the free time. But you'll understand it eventually. For now, you can accept it as yet another type of matrix. But keep in mind the connection with the least squares. That's important. Okay. So now assume that you have this equation again. and you want to find such x that y becomes as close to y star, y desired as possible. So you want y to become as close to y star as possible. Sounds, like a valid problem. Like you often have some sort of a goal. The goal itself may be unachievable, but you want to get as close to it as possible. In engineering is, I guess typical enough. So, sometimes you have to achieve the goal, but sometimes you just want to be as close as possible to it. Okay. So that is a least residual problem, right? You want to find if you substitute here, minimizing the distance between ax and y is a least residual problem. So here it is. This is a least residual solution to this problem. So this x will make sure that the distance between ax and y star is the smallest. So that is a solution to this original problem, right? But we wanted to, let's say we wanted to see what is this y that is as close to y star as possible. Well, we just multiply both by a, right? So we multiply it by a here, by a here, and this is just y, and we get this equation. So we see this is this y that can be achieved with this equation that is as close to y star as it can be. Maybe it is equal to y star. If this equation has exact solution for y star, then this would be, y would be equal to y star. But if there is a residual here, then it wouldn't be equal to, like y wouldn't be equal to y star. All right. You get the idea, right? Like this is a formula that allows us to find the y that is as close to y star as it can possibly be, given that y is governed by this equation. All right. Again, don't worry about it too much if it sounds a little bit difficult, because we are going to go through least squares one more time. But for now, you have now two ideas. First idea was that least squares solution is somehow called, this matrix is somehow called a pseudo-universe, can be found numerically in Python, in MATLAB, easily. It gives you smallest norm solution that provides smallest residual. And you can use it in this way as equation 2 to find y that is closest to y star, like, interesting. We'll use it very, very soon. So you will see why it is useful. Okay, moving on. Any questions so far?
Now it's everything.
Okay, we can go back and you can ask questions about this anytime at any part of the lecture. That is like, this material is not easy, but it's sort of designed for you to come back and reflect on it later. So, I don't want to create an impression that you have to get it as I explain it. So, if something is not very easy, you can go over it again and you can ask questions later anytime. Okay, now the main part of the lecture, the main things that I want to get through here is this concept of 4 fundamental subspaces. You'll see very soon why I started by discussing the least squares before, because it's going to be useful even for this discussion. But this is the main part of the lecture. So each matrix, each linear operator has this has like 4 fundamental subspaces, basically. Fundamental subspaces is just a term from algebra. And I understand it sounds very grand and geometrical and somehow scary, but it is not very scary. It is just, well, you'll see how we can use it, and it will stop looking scary if it does now. Basically, the spaces are null space, row space, column space, and left null space. It's a very good idea to memorize those names. As in, like, you don't have to memorize them as a rhyme, but just make sure you understand, you keep them in mind. Today we will learn those two, null space and row space, and try to make sure you understand what they are. Next time we'll go through those two subspaces. Okay, so what is a null space? Well, let's consider this rather simpler problem than what we saw before. Ax equal to 0. System of equations with a 0 right-hand side. That is the bread and butter of our linear algebra classes, even in high school. System of linear algebraic equations. You definitely solved it hundreds of times. Well, we can the problem, find all solutions to the system of equations. We can rewrite this as follows. Find all elements of the Rn space. So all x in Rn space that belong to the null space of A. That is actually equivalent. Those two equivalent formulations. So this system of algebraic equations, its space of solutions of the system, is actually the null space of A. Or yet another one, that is the first formulation, that is the second formulation, and that is the third formulation. Null space of A is a set of all vectors x that A maps to 0. So when multiplied by A, they become 0. Let me know if any of you had already studied null space in the undergrad courses. Did you?
Yes.
So some of you already had this in undergrad courses. Only you or someone else too? Okay, at least two people studied it. Great. It is a very important concept, so we would have to, we would have to understand it. You can survive, of course, without getting through it, but the bonuses that you get from knowing it as an engineer are enormous. So let's just try to understand what it is. So far, so good, right? It's just a space of all solutions of Ax equal to 0, or all elements that all vectors x that A maps to 0. Sounds good. Okay, we will denote null space as N of A. We can in the literature it's sometimes called kernel of A. And this is also a very nice formulation, null of A. So maybe we will actually use this sometimes, but I think in the slides it is N of A. Okay. So this is the, that's the null space. What is nice about null space for us as software engineers is that we can use MATLAB or Python to find it. So this expression in MATLAB gives us null space of A. In Python, it is this expression, scipy.linalloc.null space. Yep. Yep. So this expression gives us null space. So next time when you see this system of equations, Ax equal to 0, you can actually call one of those two functions depending on what you're using currently. There is obviously the same function in C++, in eigen library. So you can call one of those and you would get a space of all solutions. I don't know how far away for you the linear algebra classes are, and if you appreciate just how much of a relief it is not to have to solve linear equations by hand. But it is a relief. Like those equations are very typical for your problems, school problems, for your problems that you see in your university courses and whatnot. So it is very, very, very typical. And here what I'm saying is you can actually solve it by calling one function. What it does, it gives you this matrix N, whose columns span the space of solutions. And actually, N is orthonormal. So each column of N is a unit vector, and each column is perpendicular to all other columns. So it is an orthonormal matrix. Do you know what orthonormal, like, I just gave you the definition of orthonormal, but have you encountered it before?
Orthonormal, it means like orthogonal and vectors which has like unit vectors, unit and orthogonal vectors.
Mm-hmm. Yep. So normalized and orthogonal. Yep. Orthonormal. Great. So this is true for all orthonormal bases of this type. This, by the way, is not necessarily true. This is not necessarily identity matrix. So just you know, it's not even like a block diagonal matrix. It is something. So this is true. This is not necessarily true. Like this is, you don't know what it is. So it's important to keep it in mind. Okay.
What is N here is null space, right?
Yeah, null space. But that is true for all orthonormal matrices. So as long as a matrix is orthonormal, this is true, but this doesn't have to be true. Okay.
You mean the order matters, right?
Yeah, this is inner product. This is outer product. So inner product gives you identity matrix. Outer product gives you something. Because here you multiply columns, here you multiply rows. You know, you can think about it. You know, just mark it for yourself. Say like, think about it. It's also like things you have to verify for yourself. Just generate a couple of orthonormal matrices and see what this does. It is nice because it's nice to think about it because you can easily make a mistake here, and you will recover. But you know, learning math is about that. Like make mistake, learn, make another mistake, learn. And I'm just trying to point out where you can make mistakes so you can learn fast. All right. So that is it. That is all what null space is for us as a programmers. Just something that you can get from a library. Now, all solutions to this equation can be written like this. X star equals to nz, when z is just a number that represents the dimensionality of the null space. Let's say null space is in R n by m. So m is the number of columns. So number of dimensionality of the solution space, dimensionality of the null space. And that would be in Rm. You get it, right? So that is just a parameter. You multiply, like any vector in Rm, you can multiply it by n, you get another solution here. And what is interesting for any solution.
What is the span?
Span, yeah, that's interesting. Span of a matrix M is a space of space given by all possible linear combinations of its columns. So it is like, let's say M, let me just do it this way. Instead of M, I will write V. It will be all possible linear combinations of the columns of V. That is span. So you multiply any column by any number, add it to any other column, multiplied by any number, and so on.
So it's
all possible.
Is it summation of all possible?
Yeah, it is summation, subtraction, any linear combination. So let me give an example. So let's say you have just a vector, like this vector. There's the origin, that's the vector. So its span is all possible multiplications by a number. So this line is its span. Okay, let's say you have two vectors like this. Like this is one vector, this is another vector. Well, you can actually find a way to make, let me change the color, to make every single point, to write any single point as a combination of those vectors. For example, this point, here can be reached as, how can it be reached? For example, you scale this vector all the way here, then you subtract maybe this other one all the way here, then maybe you, what do you do? I mean, I don't know what to improvise, but basically what I'm trying to say is, since this, like the difference between those two vectors is this vector, right? You would always be like it has orthonormal component. You can actually find you know, this. I don't think I'm doing a very good job explaining this concept on this example. But basically, what I'm trying to say is that they are not collinear. So you can, if you want to move sideways, you will always be able to do it with linear combinations of those vectors. Let me give you just a simple example so you would understand.
So to finalize, span is just all possible linear combinations.
Yeah, or possible linear combinations, exactly. But let me just quickly give you like a more simple example. So it's clear? Okay. Yeah. So just as this example, sorry for wasting your time, but anyway. So like any point you want can be arrived at as a linear combination of not linear independent vectors. So here, those two vectors you can see, they give you a solution. And if it was 2D space, so everything is a span of those two vectors. But if it was a 3D space, let's say we add one extra dimension to the basis, then the span would still be two-dimensional, but they wouldn't span the whole Rn space. But any three linearly independent vectors in R3 span the whole R3. So that's the thing. Actually, span is one of those concepts that you can use to give definitions of, independence of vectors and so on. I think it's one of those key concepts that people used in older textbooks on algebra, where they didn't use fundamental subspaces, for example, like Russian textbooks. Okay. All right, so back to this equation. So you can see every solution can be written as multiplication, like we have this n null space of A, and you multiply it by some vector z, which lies in the Rm, given that n is in Rn by m. So you have this this vector that lies in the solution space, if you want, is a coordinate in the solution space. You can call it that way, and you can get any solution as this expression. And for any solution of this original equation, you can find its coordinate z in the solution space. How? Well, it's very easy. Since n is orthonormal, this is actually just that you write n transposed x, and that is how you find a coordinate of the solution in the solution space, or coordinate of x in the null space. Okay, great. That is, sounds interesting, useful. Now, so here we can repeat the same thing, but let me just quickly go through it so we progress. So again, n is orthonormal basis in the null space of A. And if x lies in the null space of A, it can be written this way, as was said previously. And that are coordinates in the basis of n. However, there are vectors which not only are not lying in the null space of A, like obviously, right? Not every vector is in the null space of A, but there are even vectors for whom the closest vector in the null space is a zero vector. Now let's digest this idea. So you can have a vector which does not lie in the null space, of course, right? For for almost any matrix except the zero matrix, there would be vectors that do not lie in the null space of this matrix. But there are also vectors for whom the closest vector in the null space to them is a zero vector. So no other vector, every other vector in the null space is further away from them. That intuitively that should make sense. Let's imagine that null space has this shape. It's a line, and here is the origin. Like null space always, same as any linear space, always contains the origin, right? There's the origin. And let's say you have a vector here. You can kind of see that the closest to it is the origin. Like it makes intuitive sense. Like for this vector, the closest to it would be something else, not the origin. But for this vector, it will be the origin. So it makes perfect sense. For this vector, it would also be the origin. For this vector would also be the origin. So in a sense, you can kind of see that there is at least a whole line of vectors for whom the closest, this is a null space here. So for whom the closest vector to them would be the origin. That might be a little bit abstract when I draw it like this, but we'll see it in numbers in just a second. So let's move to the numbers. So here's a matrix A, like this. It has a null space 1 and 0. Do you agree that its null space is 1 and 0?
Yes.
Okay.
There also could be another null space. It's not a unique null space, right?
Yeah, no, null space is unique. The basis is in the null space is given by this matrix. The only other possible basis is this matrix. You cannot find any other null spaces, the null space basis, orthonormal basis in the null space. Of course, this matrix would also be a basis in the null space, but it is not normalized. And for example, something like this is not even a basis in the null space.
Yeah, but it should be normalized. Like, sorry, basis in the null space should be normalized. Yes?
No, basis doesn't have to be normal. Orthonormal basis is unique, right? So orthonormal basis is unique up to a sign here. The not orthonormal basis, you can find an infinite number of them. So no, you were correct. It's I'm just trying to guide us towards the way we think about those things. But you were correct initially. Okay, good. So this is our normal basis. So what I think you would all agree that it is indeed the basis in the null space. Why? Because as long as you multiply this by anything and this by nothing, you would get a 0 output. And if you multiply it by anything and this by anything, you're not going to get a 0 output. You're going to get something. So it has to be 1 here, 0 here, or -1 here and 0 here. Okay, great. So this matrix here is definitely an element of the null space. How? Well, because you can multiply null space vector by 2, by -2, and you would get this element. This is also an element in the null space. So you can see those vectors, you can just prove that they are in the null space. This is a proof, by the way. This is how you prove that they're in the null space. You find coordinates in the null space, -2 and 10.
So these are possible solutions.
Yeah, these are possible solutions to this equation. Okay, this guy does not lie in the null space. How do you check? Well, it's very easy. You can just say, let's multiply this matrix by this vector. And what you get on the outside is this. And this is clearly not 0. Hence, it is not in the null space. What is the closest element to it in the null space? Well, the smallest norm element in the null space for this vector is this guy. How do I know? Well, you can trust me, or you can try to find something else. I will give you a way to do it on the next slide.
Yeah, well, why? So we will understand later why it's the closest element.
I mean, I'm going to give you like a way to find those closest elements, but you know, understand why it is the closest.
What if like 0 and 1? Is it not the same Euclidean distance?
0 and 1 is not an element of the null space.
Oh, okay.
So 0 and 1 is not an element of the null space. So out of all vectors that can be produced by multiplying this by number, this is the closest to this guy.
Okay.
It was a very good question. Like, how can you actually understand that this is the closest?
It's because, for example, our null space should look like some number and 0.
So like
No.
distance, I think.
Yeah, exactly. Well, some number and 0. Come again. The second question was.
I was asking if the closeness is measured by the Euclidean distance.
R2, yes, Euclidean distance indeed. If it was measured by something else, I think the result would be exactly the same because of one-dimensional space. I think I didn't check, but in some other cases, yes, indeed, the closeness would be completely different for different metrics. Okay, so let me just show you graphically what it is. Let's say here is 1, here is 1. This line, horizontal line, is a null space, by the way. This is a null space. This x1, x2. So I will draw this vector here as a dot, as a big dot. That is this vector. So what is the closest element to this vector on this line? Well, this guy, right? Because
0 and 1.
Yeah, because the distance to anything else is going to be bigger, right? You can kind of see it graphically. Does it make sense now? I think it does, right?
It does.
Oh, okay. Now let's consider this guy. For this guy, the closest element to it in the null space is 0, 0. Why? Well, let me draw this guy for you here. Is actually, let me choose a very bright color. It is vector somewhere here. And you can see for this element, the closest element to it on the null space is 0. Like everything else is going to be further away. All right, so for this element, 0 is the closest. Okay, good. It's nothing profound. I'm just trying to show you in terms of numbers why we can have something that some vector outside of the space, of which the closest element in the subspace to it is 0. Like it is normal, right? It's of course there will be cases like this. It makes perfect sense. So okay, let's move on. So there is a definition. The definition is a little bit scary, but is a good definition. So for a vector x, if for a vector x, the closest to it vector in a linear subspace L is a 0 vector. So if for a vector x, the closest to it element of the linear space is a 0 vector, then such x is called orthogonal to the subspace. So again, if the element is the vector is such a vector that the closest to it element of the subspace is 0 vector, then it is orthogonal to the subspace. We denote it this way: x is in L orthogonal. This symbol is called perp in LaTeX, perp, perpendicular, but we can call it L orthogonal. Okay, so it's not very very profound.
Sorry, 0 vector
Yes?
is just 0, 0, yeah, right?
Yeah, zero vector is the origin.
Yes.
So for example, here's I wish I could always draw like horizontal lines. It would be so nice. So let's say we have this subspace. I will draw it in blue. This is a linear space. So all vectors that are perpendicular to it will be orthogonal to it. Why? Well, because for those vectors, the closest element to them would be 0. Like those vectors, for example, are not orthogonal because for them the closest element would be non-zero. But these are. So, and by the way, yeah, so these are. So this is the space of all orthogonal vectors. Okay.
Sorry. Subspace L. Blue line is blue line is a subspace.
Yeah, blue line is a subspace. In this case, it is not horizontal, right? But it doesn't have to be. It can be anything.
Yeah, we can say that. Okay, so usual reference frame is some space, right?
Yep.
And this blue line is a subspace.
Yeah, the reason we have this sub is because you have Rn usually.
Yes,
That
for
is
example,
ambient space, and anything that is kind of inside Rn would be its subspace. That is the reason why we have subs there. This is space. This is a subspace.
What about, can we say that there might be many subspaces, and each subspace may have different dimensions?
Yeah, of course. Let's say you have R3. Well, span of vector 1, 1, 0, 0 is a subspace of R3. But it in itself, this span is one-dimensional. Sorry, I'm writing it badly, but it is dimensionality of the span is 1, but this subspace of 3. The span of, let's say, 2, 0, 1, 1, 0, 0 would also be subspace of R3.
But the dimension would be 2.
The binary dimension would be 2, yes. By the way, span of 1, 0, 0, and 2, 0, 0 is one-dimensional. Why? Because they are linearly dependent. So adding a second column didn't change anything. It is a horizontal line, all the same.
Because they are linearly dependent.
Yeah, because you can imagine, like, what do we mean by? I mean, I don't want to go into philosophy, like what do we mean by dimensionality, etc. But basically, how many coordinates do you need to describe any vector in this subspace? Well, one coordinate, right? You can say how many times you need to multiply this vector, like what number do you need to multiply this vector to get any element of the span? You know, like say this element. Let me do something like this element. Its coordinate is 4. You can use coordinate 4, just how many times this is multiplied by it. That's it. You don't need a second coordinate to describe elements of the subspace. -4, -40. Like, you understand, right? Just one coordinate. Therefore, it is one dimension. Okay, great. Now, hope I didn't lose all of you on those abstract discussions, but they are important. All right, so the space of all vectors x, which are orthogonal to a subspace, is called orthogonal subspace to L. So you have L, and the space of all vectors that are orthogonal to L is the orthogonal subspace, or we can also call it orthogonal complement. Orthogonal complement. So that is pretty interesting, right? Remember this example with a line that passes through the origin? Well, this guy is its orthogonal complement, this red line. If it is R2. If it was R3, it would have been two-dimensional, because there would be another line that looks at us in R3. Okay, so I hope you get the idea. Let me try to write one example in R3. I will just of orthogonal complement. That is a scary task because I think I might just lose you, but I will try to do it in half a minute. So bear with me, please. So let's say you have a line that passes through the origin again, but it is in R3. So we have this in R3. What would be its orthogonal complement? Well, it is actually all vectors that are linearly, that are orthogonal to it. So all those vectors are orthogonal to this line. So the space of all orthogonal vectors is actually all of this, and all of this, all of this, all of this. So in other words, you can write it kind of like, you know, like this plane, which is perpendicular to this line. So this whole plane is orthogonal complement of this line. And in geometry, I don't know what kind of a geometry course you had, but sometimes you talk about tangent spaces and orthogonal spaces or normal spaces, I think sometimes. So like, for example, you have a plane. You will say that the normal space of a plane is like this, you know, orthogonal line to it. Or you have a line and you say orthogonal space to it is like this plane. That is a very, exactly the same idea. But anyway, let's go back to the slides. Those abstract discussions are extremely interesting, but they run into a risk of losing your attention because they are also very difficult to follow. So I apologize for not spending a lot of time on it. All right, great. So we have this idea of orthogonal vectors and orthogonal complements. So now, or before I move on, just one last piece of information. That is, if you have a space, subspace of Rn, well, then subspace plus its orthogonal complement together span the whole original space. That is difficult to wrap your head around, not in the least because of this strange plus sign. That basically means that, you know, if you think about those as in terms of their bases, you just add their bases together. You have one basis, you add, concatenate them, sorry. You concatenate columns of their bases. If you think about it as linear spaces, you say we take every element of this space, add to every element of this space, and we get like collective new space. But what I'm trying to say basically here is that orthogonal complement is everything that is left over from this subspace. If this subspace was a line in 3D, this would have to be a plane. If this was a plane in 3D, this would have to be a line. If it was a 5-dimensional subspace of a 12-dimensional space, this would have to be 7-dimensional. A very clean way to write it is something like this. Dimensionality of L plus dimensionality of L perpendicular is equal to N. So dimensionality of the ambient space. So this is, I wouldn't be surprised if this is called a fundamental theory of linear algebra or something like this. But you know, that is just how, more or less, a natural consequence of how we defined this perpendicular thing. All right, moving on. I apologize for abstract ideas. The concentration is staggering. Now, let's say you have vector A, and you have two elements X and Y that lie in the subspace where X lies in the subspace L, and Y lies in the orthogonal complement to L. So X is in L, and Y is in L perp. Okay, so you have A, and it is given as a sum of two vectors. Okay, good. So we call X here a projection of A onto L, and we call Y here a projection of A onto orthogonal L perp, or orthogonal complement. That is the definition, if you want. That is a very kind of simple definition, but it is a definition. So X would be projection of A to one subspace, and Y is a projection of A onto another subspace. Okay. You can also, if you want to define it with more flourish, you can say projection of A onto a subspace is the closest element of the subspace to A. You can say it, right? That is also a definition.
So can you repeat that?
So you could another definition would be a projection of A onto a subspace is the element of this subspace which is closest to A. You can say it this way, but it is a little bit, a little bit. I mean, it's the same. It's the same thing essentially. Here I just wrote A as being already decomposed into two elements, and that's it. Okay. The idea of what projection is will become clear. The more you use it, the more clear it will be. So don't worry about the clarity. It's going to clarify itself. But do think about. By the way, those definitions you can find them anywhere, right? You can find them in linear algebra textbooks and so on. So you don't have to necessarily follow my definitions here. I'm trying to reformulate them in such a way that it is intuitively clear. But there will be other definitions, and they are all correct. Okay. How do you find projection of A onto a subspace? Well, actually, you can find it this way. And notice that is exactly what we saw before. So let me remind you where we saw it before. Yeah, here. This Y was the closest element to Y star. So there was this space. Yeah, what kind of subspace it was? We'll see very clearly next lecture. What subspace Y and Y belongs to. But we saw that this comes from the fact that we are trying to solve a least square problem. So we'll see it very soon, but not today, maybe.
So I have a question.
Yes, please.
L is a subspace. So
Yeah.
how do you multiply a subspace?
Yeah. When I say subspace, I refer to this squiggly L.
Oh, okay.
And L, which is bold, is orthonormal basis.
Okay.
So notation is extremely important in linear algebra. Sometimes we abuse it, but in this case, what I mean is we multiply the basis, orthonormal basis. Okay, so projection of A onto subspace L can be found this way. I would prefer, and it has direct connection with what we found previously. Let me, if you don't mind, leave it at that for now. Consider it like just as a piece of another piece of the puzzle. And next time when we study column space, you'll see exactly at least more exactly what is going on. But that is how you find the closest element. And you see kind of like before I argued very convincingly that, Y was the closest element to Y star when Y is equal to AX. All right, let me just break the rules for one time. And, I will tell you exactly what's going on. So this Y belongs to column space of A, right? What's column space of A? That is exactly what Y is a space of all possible linear combinations of columns, or simply put, all possible Ys that can be found this way. So that is a linear space, and you can kind of see it is very similar. Yep, except here L is orthonormal basis, and there A wasn't an orthonormal basis. But actually, this formula is, we derived it from least squares, and hence it is correct. So this formula is actually correct. It doesn't have to be linear basis. This formula is correct for all possible matrices. So for as long as Y is element of the column space of a matrix, and if it is given in this way, this any Y that is given this way is element of column space, we can find Y that is closest to any Y star using this formula. So here, what we can say is that X is element of the column space of L, and hence the closest element to X sorry, the closest element to A, which lies in the column space of L, is X. So that is, but we will discuss column space next time, and we will get more comfortable with it. But that is just basically how you can reason where this formula comes from. Right, and since L is orthonormal, you actually don't need to take pseudo inverse here. This is actually sufficient. Notice it is just a transposition here.
So can we say for orthonormal, maybe vectors or matrix, the inverse is equal to the transpose?
Pseudo inverse is equal to transpose, yes. Pseudo inverse. They don't often have inverses.
Okay, it's clear, sir.
So the way you can think about this, by the way, is this way. You can say, okay, we have vector A. With this operation, what we find is some coordinate of A, let's say B, in the space spanned by L, because this is the orthonormal basis. So this basically, this expression gives us coordinates of A in the subspace. Of course, the catch is that some of the elements of A are lost because they have zero projection onto L. So it will give you coordinates, but you cannot recover original L from it, A from it. You would recover the image of A onto this space. So you can multiply it by L again, and that would recover you, so this B was the coordinates of the image of A, and this would recover you the actual image itself. So the A star, or in this case, X. So that's how you can think about it as well. If you remember that this is the way you rewrite vectors in new orthonormal spaces, in like, or recover coordinates of a vector in a new orthonormal space. So, yeah. Okay, good. Just that's another formula to remember. You saw how we derived it using least squares, and this is something that is specific to orthonormal basis. Okay, good. Now, so since this is true, and we know that X is equal to this guy, we can rewrite this whole thing as such. Right? We can just substitute X here. From this, it follows that we can find Y by moving everything to the left-hand side. So Y would be equal to A minus L pseudo inverse A, which is the same as identity minus L pseudo inverse A. You follow me, right? It's pretty clear. And that is the result here. So you can find Y this way. But what was Y? Y was the projection of A onto L perp. So Y was a projection of A onto L perp. But since L is orthonormal, you can write it this way. So we found a formula for the projection onto the orthonormal subspace as well. And notice we don't need to use any separate basis here. As long as we know basis in L, we can project onto its orthogonal complement without finding the basis in the orthogonal complement. That is pretty powerful. You get the result that we got here, right? Is clear what we achieved, right?
Yes.
We achieved a projector onto the orthogonal complement. So this was a projector onto the linear space, given its basis. And here is a projector onto orthogonal complement of linear space, given the basis in the linear space. So we have two projectors now. Matrices which you can use to multiply any vector and project it onto the linear subspace. Sounds great. Now, back to the null spaces. So let n be a null space of A. Its orthogonal complement, n perp, is called a row space of A. We call it a row space. There is a reason why we call it a row space. Basically, it's the span of all rows of A. That sounds completely unrelated and very difficult to grasp, I think. But is actually a very good definition, row space of A. Yep. If you want, we can discuss this naming next week when we have in our next lecture. But for now, just remember, it is a row space of A. Orthogonal complement of n is a row space of A. So a row space is a space of all inputs to A that produce non-zero outputs. And it is a space of all, I would say, that produce all non-zero inputs that produce unique non-zero outputs. And I would say maybe smallest norm. Smallest norm inputs. Why those caveats? Well, because let's see what it actually means. Let's see what it actually means. So let's say A, X is equal to Y. Y is output. It is not zero. And so X is element of the row space, right? But let's say we have now Xn, which is element of the null space of A. Then AX plus X plus Xn is again equal to Y. So this sounds like X plus Xn is also element of the row space. But that cannot be true. Why? Because X plus Xn is not orthogonal to Xn. It has to be orthogonal to Xn because it is element of orthogonal subspace. Why it is not orthogonal? Well, if
what is Xn?
Xn is element of the null space of A.
A element.
Let me write it on the clean board so we'll just get a better idea. 1 second. So let's say you have, again, AX row equals to Y. This is element of the row space. Let's just say by definition, it is element of the row space. Okay, then, and let's say you have Xn equal to 0. So Xn is by definition, again, element of the null space. Sorry, technical issues. Okay,
Isn't AX equal Y? This is a column space. Or...
No, Y is the element of the column space. Indeed.
Okay. Yeah.
Absolutely true. R is the element of the row space. But
Okay.
yeah, but column space we'll study tomorrow. That's why I didn't want to bring it up today. But they're all extremely connected, so it's very difficult to discuss them separately. But you know, we have to for pedagogical reasons. Otherwise, it will be difficult for you to grasp all of this at the same time. Okay, so this element now, xr plus xn, is also equal to y. So you would think it is also element of the row space because it produces non-zero output. But it isn't. Why? Because any element of the row space has to be orthogonal to element of the column space. So the dot product of any element of the row space with the element of the null space has to be 0. That can also be a definition, by the way. We could define row space as the space of all vectors that are have 0 dot product with elements of the null space. Like, they're all equivalent definitions. So basically, Rn would have to be let me write it this way. Its dot product with Rn would have to be 0 by definition, because they are from orthogonal subspaces. Perpendicular vectors have 0 dot product, remember. But
so, question.
Yes.
So, is there a mathematical proof to this, or it can only be discovered by probably trying it out with numbers?
Come again. Sorry, what's called proof of what?
Of this concept that any element of the row space has to be orthogonal to the null space. Is there a way we can prove this mathematically?
It's by definition. We define a row space as orthogonal complement to the null space.
Okay. So, for example, we have XR plus XN. Usually, what we have, their combination would not be orthogonal to, would not be in the null space.
Yeah, this combination is not in the row space or in the null space. I'm trying to prove it.
Okay.
Like, you can, let me just prove it very quickly. So you would have this, which is equal to this. When we open the brackets, it will be, maybe R was not a great choice because I write it exactly the same as N, plus Rn times, or Xn times Xn equal to 0 plus this, and this is not 0, as you can see. So indeed, this element is not in the row space of the matrix A, because this doesn't hold. So a row space is orthogonal to the null space. So every element of the row space has to be orthogonal to every element of the null space. And here they're not. So that is a problem. Row space has this property of producing unique outputs. So every element of the row space would produce a unique output, but not every vector that produces an output is element of the row space. As you can see here, this vector produces y, but it is not element of the row space. But the smallest norm element that produces y is the row space, in the row space. Why? Well, because this combination clearly, let me just use a different color. This combination of those two vectors is going to be bigger norm than this vector, right? And the smallest possible combination that you can have here is when this becomes 0. You can prove it on your own. I don't know, we'll probably have a proof tomorrow. I don't remember for sure. But you can prove it easily because they are orthogonal, right? So you have basically this vector plus this vector. And the question is Rn, XR, what I'm talking about. XR, this is Xn. So what is the length of xn that would produce the smallest possible sum? That is a sum by norm. Oh, 0, of course, right? It's the Pythagorean theorem. You know, the length of xn plus xr squared is equal to xr squared plus xn squared, because they are orthogonal. If they weren't orthogonal, that wouldn't be the case, but they are orthogonal. So that is why this guy has to go to 0 for this to go to a minimum. And hence, this is the smallest possible element that produces y, this particular y. So that is the story. Again, same as everything else here, it's not super clear. Like, it's not something that you can just, oh, okay, yeah, of course. You have to think about it 2, 3, 4 times to get it completely. But you start to catch the wind where it blows, right? You see orthogonal subspaces have orthogonal elements. You can try to use those ideas for proofs. Minimum, like, you know, the closest element has something to do with solving the square problems, etc. You know, and you know basics of linear algebra. So whenever you feel like you want to prove, just write it. Like same as here, I wrote for you the proofs that smallest element that produces y would have to be element of the row space. It wasn't, by the way, a very clean proof. So, you know, you can make it cleaner if you want. All right, back to here. So we denote elements of a row space as R. Oh, sorry, we denote the row space itself as R. We can say that this R of A is equal to n perp of A, right? So orthogonal complement of null space is R, row space. Okay, good. Now, let's just see a little bit of what we saw before. So given a vector X, matrix A, and its null space N, null space is a matrix, we can check if X lies in the null space or not. Of course, the simplest check is to just check that this is equal to 0. Like if this is equal to 0, that is the simplest check. Then X is in the null space. But we can do it also in this way. We can check yeah. So how do we check it? We can check that its projection onto the row space is 0. If the projection of X onto the row space is 0, then it lies completely in the null space. So what does it mean? Well, what is the projection of the rows? Row space is the orthogonal complement of null space. So it would the projector onto the row space is given as this guy, right? This is a projector onto the row space. So we multiply it by X, and we make sure that this is equal to 0. That is the way to check it. Of course, again, much simpler to just check this condition, but we could check it this way as well.
Can we check it by equating X equal Zn?
Come again?
Can we check it by saying that X should equal Zn? Like in this.
Zn?
Yeah, like we did in the second slide here. Like we said, if Z is Z gives a unique solution for every Z. Like we check X as can be written as a combination of the bases.
Yeah, but so we have X, we have A, we have N. If we have A, we can write this condition. If we have N, we can write this condition. What is the condition that you propose to write?
X should equal Zn, like
Z, N?
Zn.
N times Z.
N Z, yeah.
Yeah, but what is Z?
Like we figured out if we equating the equation and solving for Z, if it is possible, if it does have a solution.
Yeah, exactly. Right. If you if we have some X, we can write it as N times Z times N. Oh, sorry, N times Z. Indeed, it is true. But how do we write a condition that allows us to check something? Like we can do it, of course, and we can find Z as as this. But that is only if we already know that X is a solution.
Yeah, okay.
There's not a condition for X to be a solution. That is a property of the solution.
Okay.
It's kind of like no problem. It's kind of like saying that this is the same, right? Transpose and pseudo-inverse, because it is a property of orthonormal matrix. That is not a way to check if the matrix is orthonormal. The way to check if the matrix is orthonormal is this. Not this, right? This is the way to check. This is not the way to check. But if this is true, then this is true. Okay, so if this works, or this works, then you can use this, for example. But not if it doesn't work. So anyway, in which case would you want to write expression 7 instead of this expression? In which case would you prefer to use this instead of this?
When you have the basis instead of the matrix A.
Yeah, let's say you have both. Then when?
If the basis is much smaller than A,
yes,
so it will.
Yes, indeed, absolutely correct. Let's say that the basis N is in R, let's say 10,000 by 2. So this matrix has how many elements?
10,000 by 10 by M.
So this this basis is 10,000 by 2. Oops. Can I go back? Oh, I can go back. So good. Let's say we have null space of this matrix is 10,000 by 2. What is the size of this matrix? It's a square matrix. So this is a square matrix. What would be its size?
10,000 by 10,000?
Yeah, 10,000 by 10,000, exactly, because the number of rows of N is equal to the number of rows of A. Or excuse me, equal to number of rows of N is equal to number of columns of A. Okay, now my matrix has 100 million elements. It's a big matrix. We don't want to check this condition. That is 100 million operations, right? And multiplications, and about 100 million summations. So we just don't want that. Here, what we can do is we can compute first this operation. This would be 10,000 multiplications, 10,000 summations. Then we can compute, let's say, equals to D1. Then we can compute this. This would be 10,000, again, 10,000, sorry, by 2, by 1, let's say by 1, just for simplicity. This will be, again, 10,000 multiplications, 10,000 summations. Then we can compute X minus D2, this part. This would be only 10,000 divisions, sorry, subtractions. So we managed to, instead of 100 million operations, to make do with, sorry, 200 million. Instead, we made do with 20 plus 20 plus 10, 50,000. You see just how much we can save in terms of computations. Does it make sense?
Yes, it does.
Yeah, but only if we already have n. If we want to compute n for this matrix, it's going to be very, very expensive. So, but sometimes we do have those. That happens. So, all right. Now you get the idea. By the same logic, if we want to check if the element lies in the row space, we can see if it has a zero projection into the null space. Zero projection to the null space. What is a projector into the null space? Well, it is, as we said before, this, right? This is a projector into the null space. So a zero projector into the null space would be this condition. All right, that's the idea. By the way, here expression 8 cannot be substituted with something else, right? You cannot like here you can replace it with this condition. This you cannot. I don't think. Like you can write a, oh, you can write something that would only use a matrix. That is true. We'll look into it later, but basically this condition is a good condition, like on its own right. In order to write something like this, to check row space, basically, I will just write it for you. You don't have to memorize it. It will be something like this. This would be the condition to check if the vector lies in the row space. That won't actually use the basis here, this SVD decomposition based orthogonal row basis. So you can see this condition actually looks much cleaner than this condition. Anyway, we'll look into those, I think, next lecture, if I remember correctly. Okay, we're almost done, I think. Let me just look at the following slides. So let us just briefly see what kind of stuff we can do with our knowledge. So first, we can say, let's find all solutions to this system. All solutions, right? That sounds like a advanced high school test, right? Or entrance exam to the college. No, I don't know. Like you're all from different countries, so I don't know what kind of entrance exams you had. But all solutions. Okay. So first of all, if we have two different solutions, x1, x2, we know that both of them are equal to, when you multiply them by a, let me write cleanly. If when you multiply them by a, both of them are equal to y, right? Like here. Okay. That means that the difference ax1 minus ax2 is equal to 0. Okay, so the difference is equal to 0. In other words, difference between any two solutions lies in the null space of A. That is a key fact at using algebra fundamental subspaces to find answer to this thing. Difference between any two solutions lies in the null space. On the other hand, let x star be a solution, and let xn be a null space element. Then this guy is also a solution. Why? Because we can open the brackets. This is equal to y, this is equal to 0, hence it is a solution, right? You see in this chain of arguments, we found that this is equal to y. So it is a solution. Therefore, a solution space is given by a single partial solution, which is not in the null space, and the whole null space of A. So the answer to the original task is find any partial solution that is not lying in the null space. And as long as y is not 0, it cannot lie in the null space. And then add the whole null space to it. And that is the answer. Okay, that is how you solve this problem. Now,
So where is the row space here? Like
where is what?
the row space.
A row space? You will see
Like-
it. You will see it right now. You will see it right now. So there are many ways to choose this partial solution to this equation. Remember, again, we are solving this equation. There are many ways to choose this partial solution. Since it is not in the null space, then x partial plus any null element of the null space would also not be in the null space, right? You cannot if a vector is already not in the subspace, you cannot.
Question.
Yes. Yes.
This, what is a partial solution?
Partial solution means that it is some solution of the, basically it means that axp is equal to y. So it's not like the reason people say partial is because it is just one of many solutions. There's no special properties, just one of many solutions.
Oh, okay.
Okay. Great. So what we can do is to say, let's find the smallest norm xp. Since we have a lot of them, right? We can find the smallest norm one. And there is this theorem statement or whatever. That the smallest norm x partial will lie in the row space of A. Okay. So you see, we suddenly connected back to the row space. And that is, that is a powerful statement. That the smallest norm partial solution lies in the row space. For example, it means that row space will contain only one solution to this equation. And a lot of other consequences. But let me first prove this statement, because maybe you don't believe me, right? You don't have to believe me. It is algebra class. We have to prove everything. So we can prove it by observing that there can only be one solution in the row space. Why? Well, because as we said, that if we have two solutions, P1 and P2, the difference between those solutions has to lie in the null space. And we cannot have two elements in the row space whose difference lies in the null space, because linear combination of any element of the subspace is still in the subspace. That is a fundamental property of linear spaces. So there can be only one solution in the row space. That is very interesting. And adding any vector from the null space to this solution that lies in the row space can only increase its magnitude because of the property of Euclidean metric or of whatever you Pythagorean theorem, right? What is here's the sum of two vectors. What is this? How do you choose this vector in order for this vector to be the smallest norm? Well, this has to be 0. This has to be 0. If it is not 0, the norm of this vector is always going to be bigger than if it was 0. So since they are orthogonal, okay. Therefore, therefore, the smallest norm solution has to lie on the row space and is a single one. There's only one. So that is a story. That's how you can prove that it lies on the row space. Questions? Sorry, I'm any partial. Sorry, I didn't check the chat as often as I should.
It's clear, sir.
Okay, it's clear. Let me get back here. Oops. Last slide. So, just a little bit more of your attention and we'll go. So if we have a solution to this equation, we have x star, which is a solution to this equation. We can find this particular solution, a smallest norm particular solution. Let's say smallest norm. Particular solution by projection. Now, please appreciate it for a second. We spent this whole time talking about least squares, subspaces, projections. It was abstract, borderline interesting. Now suddenly we can use this language to instantly find something extremely useful, like the smallest norm solution. And we don't need any extra effort now because we already spent all the effort that we had to. So smallest norm particular solution, how do we find it? By projection. We know that it has to lie in the row space. We just proved it. And we know how to project onto the row space. How? Well, like this. We did it before, right? This is projection onto the row space. And that is a particular solution. If we don't have n, we can also do it this way. I didn't prove this formula. You can try to prove it if you want. The way to prove this formula is, by the way, also through least squares. Almost everything is in those projections is done via least squares. So if you want, you can go ahead and prove it. But anyway, that's how you can prove that particular solution. Sorry, that's how you can find the smallest non-particular solution. And that is, by the way, something that you can encounter on a test. You are not going to, because the tests are over for you. You are too old for that. But in the old days, you could have encountered something like that on the test, like find the smallest norm solution to the system of equations. And you just find any solution, and then you can do this in Python. And that is very, very fast. So now you're going to encounter those things when you do your research and when you have to find, let's say, smallest control input that produces desired output. Let's say you have actuators which are not doing, like some of them are linearly dependent. For example, if you do parallel robots, stuff like this, you would find infinite number of ways to achieve the same result. What is the smallest norm input that achieves the same result? Well, here. What is the space of all possible inputs that achieve the same result? Well, this plus null space. See, it's very useful. Alternatively, we can find it simply as that. And we came all the way back to our least squares. So if this is not too expensive, we can just do that. If if it is expensive, we can do that. Depends. But now you have two ways to find your smallest norm solution. So all solutions are then given in this way. That is how you can find all solutions to the original equation. Or of course, if you you can keep this guy here and substitute here. So that way you won't have a matrix in this expression. So that is it. That's it for the class.